Once again, welcome back to all of you. Uh, Today, we are going to discuss third theorem on isomorphism. In the last lecture, we discussed about second theorem of isomorphism. So, of course, the third theorem is seen what it says, and we also proved some lemma which is going to be used or useful while proving third isomorphism theorem. So the statement was that if we have a group and there are two subgroups which are normal in that G, suppose G is its group and H and K, there are two subgroups of G and they are normal in G. And along with the consideration that H, that is these two subgroups, one is contained in another one. Okay, so if H is contained in K, you may also consider K is contained in H. But the thing is that in that case, role of K and H will be swept. Okay, so if this holds, then the quotient group G by K is isomorphic to the quotient group G by H with the quotient group. This is K by H. Okay, K by H. So this is what we are supposed to prove. So in order to prove this, we have seen that this thing should be well defined. Okay, these things. I think I mean to say that we have some right or full right to talk about this quotient group, this quotient group, this quotient group. Of course, because K and H are normal in G, so it is natural to talk about the quotient group G by H and G by K. So we have this and this. These two things are available to us readily. And as per the lemma we proved yesterday, if these conditions, if under these conditions, okay, H becomes normal in K, and therefore K by H is also, this quotient group is also defined. And we also proved that K by H, this is a subgroup as well as, or in more precisely, we can say that this is normal in G by H. So we have all authority to talk about G by K, this quotient group, G by H, this quotient group, K by H, this quotient group, and this is as a complete. Okay, if we denote this by suppose S and this by T, so we can talk about S by T, that is this is T is normal in S. So we can talk about the quotient group S by T. Okay, so these are the things we pointed out yesterday. So let us see how we can prove this result. So of course, because we have a first theorem and second theorem on isomorphism, we have seen the proof. So we can use them, we are going to use them here. And for this, because we need to prove that they are isomorphic, so we need to find a map F from G to G by H and K by H, this quotient group, okay, which is onto and homomorphism, okay, which is onto and homomorphism. If such a homomorphic morphic function exists, then we say that G kernel of F is isomorphic to G by H with quotient group K by H. All right. And finally, we will prove that this is nothing but this is kernel of F is going to be K. Okay. Or else we can define a map from G by G by K to G by H. Okay, we are also defining map from here to here. A map F, which is then we can prove this onto and as well as homomorphism. Okay, then in that case, G by K, G or G by H, G by K, whatever you say, G by H is isomorphic. G by H is isomorphic to G by K, and this should be divided by kernel of F. And one more thing, either you can define a map from G by K to G by H, or else you can define a map from G by H to G by K. Both way you can proceed. Okay, but thing is that you need to know how you are going to proceed, and you should follow all precautions. That is to whatever function you are defining, it should be well defined. All right. So these things you need to take care. So let us write the statement and then we can proceed for proof. So theorem is that theorem says that if H and K are normal in G and H contains K contains H, that is H is a subset of K, then G by K is isomorphic to the quotient group G by H by K by H. All right. So this we need to prove. So let us proceed for proof. So we are going to use directly the implications of the lemma, what we discussed yesterday. Okay. Since H and K are normal in G, it follows that sorry, it is natural to talk about, or we can talk about the quotient group G by H and G by K. Also, we have or we can prove. See the last lemma. Of course, you are not going to write last lemma in exam. Of course, you won't be getting direct this kind of result to prove. Okay, so there should be some twist. You won't be getting anything directly in examination. So just for the sake of completeness, I'm writing here. So we have K by but we can say that H is normal in K and K by H normal in G by H. Okay. So you can refer to that lemma. So therefore, every quotient group here has a very, I think, has meaning. Okay, it's not like that H is some subset only or some subgroup, and then we are going to talk about quotient group. Of course, the quotient group we can talk about if H is normal in G, K, H is normal in K, H is K is normal in G. Then okay. So now define a function f, from G by H to G by K by, how we can define? You see here the elements in G by H are of the form, either you can take a right quotient or left quotient. Let us take right one, Hg, such that G belongs to capital G. Okay, so they have an element of this form. So any element here is of this form, fine. So F maps HG, and what about here? Because G is also here, because K is normal in G. So element in G by K are of the form, elements in G by K are of the form Kg, okay, for all G belongs to capital G, fine. So we can associate this Hg by Kg for all G belongs to capital G. All right. So because this is this function we are defining, so we need to verify that this is well defined. F is well defined. It is well defined. How it is well defined? So to prove that this is well defined, it means if same elements should have same image. That is no single element can have two images. Otherwise, in that case, it will not be a function. So when we are verifying that a function is well defined, it means we are just checking that, of course, that is a function. Really, that is a function. It is not like that we are defining something, some relation, and then we are claiming then we are treating them as function. This kind of function is not possible in real analysis, but in complex analysis, we used to talk about multi-valued function. So in that case, a single element used to have more than one image, 1, 2, 3, 4, 5, something like this. Okay. So of course, when you study complex analysis, you will see. Okay. But in real analysis, only single function is single valued only. Okay. In complex analysis, we talk about multi-valued function, not here. Okay, so let us take two elements, hg1 equals to hg2. That is, there are two. We are considering two elements from here. For g1 and g2, they are members of G. And because they are right cosets, and right cosets are equal if and only if g1 inverse g1 g2 inverse belongs to H. Okay. G1, G2 inverse belongs to H. And because H is a subset of K, so G1 times G2 inverse is also member of K, as H is a subset of K. Okay, you should remember this one. And therefore, because G1, G2 inverse is a member of K, so we must write KG1, this quotient is equals to KG2 inverse. Okay. Sorry, not G2 inverse, not but KG2. Okay, KG2. And by definition of this function, function f, we have f of hg1 equals to f of hg2. All right. So if that is the same. That is, I mean to say that any element cannot have two images. So therefore, this is really a function what we have defined. So now we need to prove that f is a homomorphism. F is a homomorphism. So to prove that, we need to consider any two elements here in G by H, and then we need to prove that this function is operation preserving. So let us consider, let capital X, capital Y belongs to, I think H, G by H, okay, G by H. So this implies that H has the form H. Either I can write X or Y. Let us write X, HX, and capital Y equals to H, Y for some X and Y belongs to G. Okay, so now consider fxy. This is equals to f and hx hy, and we can write it because hx and hy both are right coset, and h is normal in G. So therefore, product of two right coset is going to be another right coset hxy, and by definition of f, we have this is h, and hg is mapped to kg. Okay, so by definition of this, we have kxy like this. All right, and because k is normal in G also, so we can write kx and ky. And by definition, then by definition of f, we can write it like this: hx and fhy. All right, and of course, this is equivalent to f of capital X, f of capital Y. So f is a homomorphism. F is a homomorphism. So this implies that f is a homomorphism. F is a homomorphism. So therefore, by of course, we can claim that now that f is onto also. F is onto, and once we prove this, we establish this fact that f is onto, then we are prepared to use first theorem on homomorphism. Okay. So let us see. Let us see how we can prove that f is onto also. So for this, what we need to prove, corresponding to each element here, we must have some element here. Okay. Of course, any element in G by K in this quotient group has this form, and G belongs to capital G, and therefore there is an element Hg in G by H. Okay, which is pre-image of Kg. So we can take some element that is a Kg belongs to Kg belongs to G by K. In this G by K, I think K G by K. Okay, G by K, and G belongs to capital G. Okay, then Hg belongs to G by H, such that f of Hg equals to Kg. So this establishes that f is onto as well. Therefore, by fundamental theorem of homomorphism, we have now you see that f is a onto homomorphism from G by H to G by K. So fundamental theorem of homomorphism implies that G by H by kernel of f is isomorphic to G by K. All right, is it okay? Okay, so this we have as of now, and we are supposed to prove that G by H here K by H is isomorphic to G by K. Okay, so you see here what is our target here. G by H here. Okay, G by H is what we proved until now. G by H by kernel of f is isomorphic to G by K. This is we have proved. Okay, so now to establish this result, we need to prove that kernel of f is nothing but K by H. Okay, so that let us see how we can prove. So now we claim kernel of f is equals to K by H, this quotient group. Okay. So here kernel of F is a collection of all those elements of G by H such that F of Hg is equals to identity element of this. Okay, so in quotient group identity element is K here in K. Okay, this should be equals to K. So K is identity of G by K. Okay, now let Hg belongs to kernel of F. Then F of Hg equals to K. This implies that Kg by definition F of Hg equals to Kg equals to K. It means what? What we can conclude from here? Any guess? Any idea? Hello. Hello.
Yes, sir.
What we can conclude from here? Kg equals to K. Hello. G is getting absorbed in K. It means what? Don't you remember? H A equals to H if and only if A belongs to H. You forgot. This implies that what? If you don't remember and don't revise the things, how you will survive? I don't know. Over. So G belongs to K. All right. So this implies that Hg is a member of K by H, and conversely we can write like this. Okay. So this means Hg belongs to kernel of F and Hg belongs to K by H and conversely. So this implies that kernel of F equals to K by H. Okay. And therefore, suppose this is star. So therefore, from star and star dash, we must have G by K is isomorphic to the quotient group G by H with G by K by H. So this completes the proof. Okay, do you have any doubt until now? Hello.
Yes, sir.
Yes, sir means what? You have doubt?
No, sir, no doubt.
Okay. So we have seen so many results on group homomorphism and isomorphism. One example, let me quote here. One example, for any group G, G by the group identity, that is we are going to take only one element here, identity element is the only singleton identity element here. Okay, So this is isomorphic to G, or equivalently G by G is isomorphic to the group identity. The group having only one element, that is identity element. Okay, or the group generated by identity. So if the some group is generated by identity, then that group is going to be singleton only. Okay, so that is a cyclic group of order 1. This is cyclic group of order 1. Okay, so how we can define? We can define a map I from G to G by Ix, that is identity map. Ix equals to X for each X belongs to G. Then I is and of course onto homomorphism you can very much verify. Okay, so this implies that G kernel of identity, this map identity is isomorphic to G. Okay, now we find the kernel of I. So kernel of I is equals to, it is a collection of all those elements of G such that I of X equals to identity. I of X equals to identity. Okay. All right. So this is equals to all those elements of G such that Ix is nothing but X by definition. This is equals to identity. So X is going to be identity only. So that element, this set contains only one element, that is singleton identity. Okay, fine. So therefore we can write it like this, is isomorphic to G. Okay, so this quotient group has the same number of element as G has. Okay, fine. Or otherwise, if you want to prove this result, then you can also define a map from G to this group. Okay, so second part, if you try, so we can define some f function f to singleton E. So this is going to be a constant function. For every value, every element in G is going to be mapped on E, that is identity. So fx equals to E for all x belongs to G. Then f is, of course, this is not 1, is, and also we do not require 1-1ness here while using the fundamental theorem or first theorem on isomorphism. So f is onto and homomorphism as well. This implies that G kernel of f is isomorphic to this group with only identity elements. Okay, now kernel of f contains all those elements of G such that f of x equals to E. So this is equals to all those elements of G such that fx is what? Fx is E equals to E. We are going to, okay. And you know that every element of G is mapped to E. Okay. So therefore this is equals to all elements. For all elements of X, it belongs to G. E equals to E is always true. So this is going to be G. And therefore this implies that G by G is isomorphic to this. So this is a very interesting result. And of course, you also note that we are not demanding about the order of anything about order of group G, whether it is finite or infinite. All right. So this you should take care. Okay. So in this connection, let us see one more thing. one more result. You can try it out to prove. Let R be the set of real number, capital R be the set of reals or real numbers for A, B belongs to R such that A is not equals to 0. Okay. Let FAB is defined from R to R by how we are defining FAB. This is acting on X equals to AX plus B. That is, it is going to give us a linear equation. Okay. Now let G एक ग्रुप हम डिफाइन करते हैं इस मैप का contains all those elements of all those functions from R to R, that is FAB, such that AB belongs to the set of real number. Of course, A is non-zero. Otherwise, this is going to be a constant function. Okay. So in case of constant function, फिर हम यहीं पे पहुंच जाएंगे, जो ये वाला था ना, यहीं पे पहुंच जाएंगे, इस conclusion पे पहुंचेंगे. So and A is not equals to 0 and B is a real number, and N is a collection of function of the form of 1b, that is A we have fixed as 1, F 1b, and we are taking this from G. Okay, this from G. So FAB, all FAB belongs to G, and we are considering a subset of G by fixing A equals to 1. By fixing A equals to 1. Okay. Then prove. First, what we need to prove that N is normal. And remember, this is not natural number, but this is a subset of G. It is a normal subgroup of G. Second, normal subgroup and G by N. That is, when N is normal, then we can talk about the quotient group. And this is isomorphic to R star. R star, that is this group under multiplication. Okay. So I'm leaving it to you, and you can solve it and you can send to me. Okay. So this is exercise problem for you. Fine. Let us take another example. Next example is you are going to get this kind of questions only. Okay, the what I'm explaining now. Let G be a group. Or let us write like this. Let G is a group of set of real numbers, and under addition, and of course a set this is Z is a subgroup of the set of real number. Okay, this is also under addition. This is a subgroup, of course, of G, that you know. Okay, subgroup of G consisting of all integers, and under addition, both are under addition. Okay, both operation of group and subgroup should be same. Then we can say G by or R by. Let us write. It is understood that when we are taking R plus, it means we are talking about group under addition, and Z is also under addition. And one thing you know that Z is normal in Z. Okay, Z is normal. Sorry, R is Z is normal in R. So we can talk about this quotient group. and this is isomorphic to, this is also isomorphic to the set of all complex numbers with absolute value. So this is equals to G. In fact, let us write G star. Let us write it G star, and this G star is nothing but a set of complex numbers such that each complex value has modulus 1. Okay. So this you need to prove. Okay. Fine. Or you can also say this like this, that is a C star, because of course Z is not going to be 0 because modulus of 0 is 1, and C star under multiplication with all values of Z having modulus 1. So this C star is a collection of this. Okay, right. So this is the thing you need to prove. Okay. So let us see one more example. Show that any two cyclic group of the same order are isomorphic. So if the two groups are cyclic, then we need to see their order. If their orders are same, then they are going to be isomorphic to each other. All right. चलिए ठीक है. So you know one more thing, that homomorphic image of cyclic group is cyclic, and homomorphic group image of abelian group is abelian, and therefore this is also true for cyclic group, that is isomorphic image. Cyclic group, and when we are considering isomorphism, so in that case we can say that isomorphic image of a cyclic group is cyclic. Isomorphic image of abelian group is abelian. Okay, so you can try it. And rest thing we will see some more examples in forthcoming classes. Okay, then by that time, bye-bye.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.